大家的踊跃发言跟提问。Now let's welcome Professor Thomas Canhao Xu to make the first keynote speech. The speech title is Hardware Software Code Sign of Efficient Deep Learning Algorithms. Welcome.
All right. Hello, everyone. Can you hear me? Hello, everyone. Can you hear me? Okay, good. So I'm now trying to share my slides. Can you see my slides? Can you see my slides?
Yes, Professor Xu, we can see your slide.
That's good. All right, so let's move on. So my topic is about hardware-software co-design of efficient deep learning algorithms. So I'm Thomas Canhao Xu, so you can call me Thomas. I'm from the Beijing Normal University, Hong Kong Baptist University, United International College. So short for UIC, all right? So first, something for myself. So I got my Master of Engineering degree 2007 from Zhejiang University in China. And later on, I got my PhD degree 2012, about 10 years ago from Finland. And during the 10 years, more than 10 years, about 15 years, I worked in University of Kyoto, Suzhou University, and now in UIC. So I taught over 20 courses, and I started my research since 2008, over 80 publications, and participated projects, over 15 projects. Also, I've been associate editor of several international journals. So, and of course, it's quite easy to find my information. In fact, you can just put my name in Google. I think you can find some results. I think the number should be higher. I think they should get something over 200,000 results from Google. Or you can put my name in Baidu. You can get tens of thousands of results. My Chinese name, of course. And you can find some of my media interview from China, also from overseas as well. So I don't want to talk too much about this. So, well, I think the easiest way is to search from the search engine, right? Like Baidu or Google. So, okay, so what we are trying to talk for today is about deep learning. And well, this kind of topic is very hot nowadays. For example, for the deep reinforcement learning, especially this year, the ICLR conference, I think the hottest topic is deep learning. So that's number one. And after that, we have the reinforcement learning, and we also have the representation learning and a lot of other learning stuff. So basically, these topics are the most important, well, or let's say the hottest topics for us now. So, well, I think, of course, there is a reason for that, right? A few years ago, we have the so-called the AlphaGo, so beating the Lee for the Go game. And starting from that time, we all know that the deep learning, the machine learning is super important and super useful. And the AlphaGo, in fact, it's based on the DZN. So it's basically a residual network. We now know it's ResNet, super useful. Besides the ResNet, it's also got the Monte Carlo tree search and the reinforcement learning. So this is the main architecture of the AlphaGo, and starting from 2016, they have the first version of the AlphaGo, beating Lisadol for over 1, and 2017, the AlphaGo Master, it's even stronger beating Kejie 5/0, and basically there's even a AlphaGo 0 and AlphaZero later on. So basically, well, it's already very difficult for us to beat the computer for now. So, well, I think we now have the Mu0, the so-called Mu0, the latest version. It's published December last year in Nature. So basically, it's able to learn not only from the Go game, but also from the chess, from the shogi, from the Atari games. So basically, well, if you just give a game to the let's say AI, then basically it's able to learn from the game, how to play the game, how to interact with the environment, and how to win the game, of course. And it's doing pretty well. It's doing pretty well, and can beat a human most of the time. So I think it's already pretty awesome. So that's only one thing. The other thing is that the same team, DeepMind, they also developed some kind of other AI to play the other games instead of the chess and Go. They also play the StarCraft game, for example. This is a very important, very, let's say, famous strategy game. So basically, you have to control your army, you have to harvest the resource, you have to build the units, you have to upgrade your science, your well, you have to control your forces to defeat the enemy. So a lot of things to do. But anyways, the AlphaStar game, the AlphaStar AI managed to beat the best human players with some constraints. They use this kind of residual network, also the LSTM, the long short-term memory, and some other things, transformers combined together to beat the world's best players. So that's another achievement for the AI. And recently, there is this protein folding. So it's again very important task. It's more than playing games, but we have something more practical or useful to the mankind, of course, because of the coronavirus, for sure. So, for example, now, well, this is very special domain knowledge because you have to know how the protein works and about the amino acids and those bioinformatics. But anyways, it seems like that the AlphaFold AI already managed to solve the protein folding problem, achieving over 90% of accuracy in this protein folding prediction. So it's already pretty awesome. I think today is 23rd of July. So last week, in fact, last Thursday, 15th of July, they published their paper in Nature magazine. So I think this is a very awesome achievement because not only they published their paper, they also released the source code in GitHub. So you can take a look at their source code and how the whole protein prediction works. But basically the whole architecture is based on the transformers, but it's quite complicated compared with the transformers we used. So we have to spend some time in researching this kind of data. And of course, the architecture and their data architecture, you have spent, I think, at least several weeks to understand everything. So this is very recent research. In fact, just last week. So those are quite awesome work. And also the deep learning, reinforcement learning are used in NLP, the natural language processing. So for example, the BERT is already proposed by Google several years ago. So this is the so-called deep bidirectional transformers for language understanding. It's better for us to understand the language, the meaning of the language. It's very useful for interactive conversation, for translation, and a lot of other things. This is open source, so everyone can use it. Later on, there's this GPT-3 last year, generative pre-trained transformer, also based on the transformer. So this one is pretty huge model. So 175 billion parameters, and it is not open. I think it's owned by Microsoft. So, well, this is quite big already. It's quite huge model. So they will use it for some, maybe some conversation uses. And of course, since language model is like, well, of course, it's language. So that model is optimized for English language. And of course, we have several models for Chinese language. For example, Alibaba, they have proposed this PLUG or plug. So this is a kind of a language understanding for Chinese. Also, they propose this Alice Mind. So they have this collection of encoder, decoder. So they have this demo lab, the 达摩院, right? So encoder, decoder, transformer, those are the basics for the model we have now. And I think just 2 months ago, Tsinghua University and the Beijing Academy of Artificial Intelligence, they proposed this Wu Dao model as well for Chinese. I think both of those models are bigger, larger than the GPT-3, but it's quite understandable because, you know, it's, well, latest, so it should be better, right? So it doesn't matter what kind of things we have. We have the AlphaGo, we have the AlphaStar, we have the AlphaFold for a lot of different things. We have the computer vision, we have the natural language processing. But anyways, we develop those things based on the machine learning and deep learning frameworks. So we have to use one of them. So maybe most of the people would choose the TensorFlow or Keras. Someone would like to choose, for example, the PyTorch or MXNet or Caffe. So, well, of course, you have to think about not only the model, but also how to deploy the model to the real hardware. For example, we have a lot of different kinds of hardware. We have the CPU, that's okay, but too slow. We have GPU, Nvidia, of course, most of the time. We have the FPGA, well, and also we have the NPU, the neural processing unit. So from time to time, you can find these things in your mobile phone. So the key for using the deep learning or AI model is that you have to deploy your model to make it realistic, practical. So that's the hard thing. That's the difficult part. So we have to find a hardware device to run your model. And this is not very easy. At the beginning, for example, the AlphaGo, they require a lot of GPU and CPU to execute the AI model, the deep learning model, which is not very good for our practical use, of course. So later on, people propose this TPU, or let's say the Tensor processing unit. Google proposed that. So, well, it's kind of a special processing hardware, especially optimized for machine learning and deep learning, this kind of programs, of course. So once you think about the embedded device or some devices with limited computation capability, then of course there are a lot of issues. There are a lot of issues, practical issues. So you have to think about, do you process those data locally, or are you sending those data to the online server, or you do both? So you have a hybrid processing pipeline. It's totally depending. And most of the time, you have to think about the use case. You have to think about the use case. So, for example, this is a very good application for deep learning. I think most of you understand that Tesla, they proposed that they can do autonomous driving. This is their internal video showing how their, for example, how their AI model works. Well, it seems it works pretty good. Well, it can recognize those cars and the lanes of the road, and even the traffic sign, stop sign, and they can stop the car, they can wait, they can see if the car passed already, and it seems pretty good, right? But pretty good is not good enough for, especially for autonomous driving. So you see that it's okay for the lab. It's okay if we test it in the lab, that's fine. But if you really want to have the real autonomous driving, the level 5 autonomous driving, means that you don't need the driver at all. So we don't need to focus, we don't need to take care, we don't need to stare at the AI to see if it's making stupid decision, then I think it's still quite far away. So basically, we still don't totally trust the artificial intelligence. I think you heard a lot of news about how Tesla autonomous driving behaves in some kind of situation which we should understand totally easily, but the car just crashed into some kind of truck or some kind of wall. So it's totally not very easy, right? And it's only in the kind of few milliseconds. It's only in few milliseconds. So I think it's not feasible to send the data to the cloud and ask the cloud to process the data. So for example, for Tesla, they have installed a computer, basically a especially optimized computer in your car. So basically every Tesla car, you can find some kind of computer hardware, something like this, all right? It's not totally the computer we have, like a server or a desktop. No, not like that. We don't have GPU. We have a specially designed processing unit for processing the image. But even for that, it's not very reliable, all right? It's not very reliable, okay? So, you need hardware inside your device, right? If it's a car, then you need some kind of hardware inside your car. It's impossible to upload those things to your cloud. That's totally not feasible, totally not feasible. So that's the case. And also you have a pretty powerful, for example, system on chip. For example, the A14, the mobile phone, you have this kind of processor in your mobile phone as well. So they are possible, it's possible to process, according to Apple, 11 trillion operations per second for the machine learning controller. So, well, but this is only a phone, right? We don't trust it in mission critical scenarios, right? And also, for example, Nvidia, they also proposed a lot of optimization for their hardware. For example, they have this so-called Tensor RT. So this is a framework to convert the different models, let's say machine learning models, to the models running on their hardware. For example, if you have a Tesla GPU, if you have a Drive AGX, that's an autonomous driving unit, if you have some embedded devices, then you can let's say deploy the model from PyTorch, from TensorFlow to, for example, to the actual hardware. So the hardware software co-design is critical for the whole process. And the latest Tensor RT8 brings the so-called BERT, large inference latency, down to 1.2 milliseconds. So which means it's quite practical because speed is very important, especially for this kind of non-critical, at least for our language understanding. It's not that critical, right? Compared with the autonomous driving, for example. Autonomous driving, we need better accuracy, maybe, but for language understanding, a little bit lower, maybe not that bad. So that putting everything together, you know that, well, indeed, the software, the model, the algorithm is important for sure. But nowadays, we know that the hardware, of course, is also pretty important if you want to make things working. So that's our one part of our research, all right? So our research focused on the optimization for the both parts. So why we say that this is the co-design, right? This is the co-design. So hardware, software co-design. So when you're designing a model, it's not only the hardware side, it's not only the software side, but we are talking about both sides. So we have both the hardware and software sides. So based on these, we have several projects for example, from different province and from the national level or from the university level. So those are some deep learning and high efficient machine learning, this kind of algorithms and co-design and this kind of projects. And besides the academic projects, we also got some projects from the industry. So, but those projects are confidential, so I cannot share too much details about these kind of things. But it's about robots, all right? You know, robots, people want to deploy those robots to real use. But the problem is that, you know, robots is a very limited kind of hardware. So basically the computation capability is very constrained. So you have a very limited hardware resource to use. So if you develop a super, let's say, a super expensive algorithm, a super slow model, then it's quite useless in the robot. So it must be fast, efficient. So this is a very tricky part, all right? Because you cannot say that I will upload everything to the cloud and wait for several seconds to download the result. That's very bad user experience. Especially think about you don't have the internet, then it's not working at all, right? So this is a very different area. So as I said, most of the time you have to think about the use case. You have to think about the use case. But the key idea is that offline processing is very important, right? Offline processing is very important. So to put everything together, of course, at the beginning, we always think about how to have a better model, how to have a better accuracy, how to have improved percentage. For example, the error rate should be lower and the accuracy should be higher and things like that. We always want a better model in terms of accuracy. This is one good part. But on the other hand, we have to think about the deployment, implementation. So anyways, your model is executed in some kind of hardware devices. So, well, in this case, you have always to think about the co-design. So when you are designing, when you are implementing the model, you have to think about both ways, all right? Both aspects to make a usable and ubiquitous machine learning, deep learning, let's say model or algorithm, okay? So I think that's about my talk. So if you have any question, you can contact me by sending me email or any email you wanted. Okay, thank you very much. So any questions?
Thank you very much, Professor Xu, for your inspiring report. Thank you very much, Professor Xu, for your inspiring report. Time for Q&A. Any questions? Any questions? Or if you have any questions, please raise your hand. The button is on the bottom of the right corner. Any questions? Okay, if you have any question, you can, or if you prefer private communication, you can directly drop an email to Professor Xu and he will answer you. 大家如果有什么问题的话，可以发邮件给许教授进行提问，许教授会一一为大家解答的。Next, welcome Professor Yin Yang to make the second keynote speech. The speech title is Opportunities and Challenges of Intelligent Manufacturing. Welcome.
Okay, can you hear me?